Hi, I'm Susan Swain, host of C-SPAN's Q&A, where we spend an hour with nonfiction writers and historians who add context to today's news. In this episode, two space scientists help us understand the significance of two space-related stories recently in the news. In our first half hour, Barnard College astrophysicist and author Janna Levin, who researches black holes, shares details about the newly released image of Sagittarius A star, a supermassive black hole at the center of the Milky Way. Then, University of Southampton geochemistry professor Jessica Whiteside gives us an update on the progress made by NASA's Perseverance rover in its search for clues about life on Mars.
At its heart, towards the constellation Sagittarius, is Sagittarius A star, the supermassive black hole suspected to reside there. A source that has been a focus of intense astronomical studies for decades. Observations of stars orbiting around it revealed the presence of an object that is very massive, 4 million times the mass of our sun. But until now, we didn't have the direct picture confirming that Sag A star was indeed a black hole. Today, the Event Horizon Telescope is delighted to share with you the first direct image of the gentle giant in the center of our galaxy, Sagittarius A star.
Dr. Janna Levin, that was the event in Washington, D.C., as scientists all around the globe revealed the first images of Sagittarius A star. You've made a study in your career of black holes. What was your reaction when you saw the first images of it?
It's pretty thrilling because we are in orbit around that black hole as surely as we're in orbit around the sun. And, you know, it's part of our reality. It's part of the universe that we live in, but not abstractly. We literally orbit that black hole, our entire solar system together. So it was something, I think, very moving to see it, but also that the entire globe paused together to look at this image of the black hole that we orbit. So I found it very thrilling.
We heard a little bit from Dr. Ozel about Sagittarius A star's characteristics. Can you tell us a little more?
Mm-hmm. Sure. So the black hole is supermassive, meaning we know of black holes that are 10 times the mass of the sun, 30, 50, 100 times the mass of the sun. This black hole is 4 million times the mass of the sun, but it's not 4 million times the width of the sun. So if you imagine the sun on the sky, it's about less than 20 times the width of the sun. So it's very small spatially, but very heavy. And it's 26,000 light years away. So imagine taking something less than 20 times the width of the sun in the sky and pushing it 26,000 light years away. So we liken it to our eyes, from our perspective, the size of a piece of fruit on the moon. So it's very small, but it's very heavy.
So did the imaging tell us, as we heard in the clip of the outside, it's been studied for decades, but did the imaging actually tell the scientists characteristics of this black hole not previously known?
That's an excellent question. That's, of course, what we want as scientists. We don't just want the thrill of laying eyes on it, but I think that that's a human element that we have to acknowledge is really important to us, and it helps us share the discovery. But we do want to make new discoveries, and we did know that the black hole was very heavy. We knew its mass from the previous Nobel Prize winners just a couple of years ago. Andrea Ghez and Reinhard Genzel, for instance, who had studied stars orbiting this nothingness, and they couldn't take a picture of it, but they had most of the characteristics. I think what we're going to get, if not at this round, what we're going to get with further studies will be the spin of the black hole, which is actually really crucial and fascinating, and maybe a measure of the magnetic fields around it, because black holes are intrinsically dark except for the material around them. And that material is luminous because of electromagnetic fields. So these are the details we'll drill down into over the coming years. But for right now, I think what we got was a confirmation of the technology, a confirmation that the black hole is indeed there, that the shadow was cast by the bright light around it, and we go forward from here.
NASA has also released something that's described as a sonification of another black hole. This one is at the center of the Perseus galaxy. Excuse me. It's this is a 30-second clip, but I wanted to play it because it's really rather mystical sounding, and have you tell us what we're listening to. My colleagues here said it sounds like the recordings of whales under the sea. What makes these kinds of sounds?
Magic. Well, technically, the sonification is completely imaginary in this example. So what they're doing is they're taking light waves, and light has different frequencies. Our eyes perceive really short wavelength light or high frequency light as blue, and low frequency light as red. And what it's doing is it's taking light that our eyes can't see at all. Namely, I believe that this is Chandra data, which is an X-ray satellite. So they're taking X-rays, which is very, very high energy light that our eyes can't perceive. And it's taking the frequencies and translating them to the frequencies of sound. So it's just a map that's being made. Technically, that black hole isn't making sounds. So it really, what we're listening to is a different way of perceiving high energy X-ray light. But there are black holes that actually make sound. And the Nobel Prize a few years ago, again, this has been a century for black hole discoveries. This century has been like amazing for black holes. There was an experiment prior to this image of the black hole that we're discussing today that measured the collision of two black holes. And what happens is when black holes collide, they're kind of like mallets on a drum, and the drum is space itself, and they ring space-time. And that ringing of space-time, that ringing of the drum, can travel basically unimpeded for 1.5 billion years or several billion years. In the case of that discovery, it was 1.5 billion years. And we recorded it with a very sophisticated instrument. And that is very close to sound. If you were floating near those two black holes, the ringing of space-time could conceivably ring your ear mechanism. And it happens that the collision of two black holes happens in the human auditory range of frequencies. And that's just a fluke. So black holes can make sounds.
So I'm going to back up a little bit because I want to have people who are listening understand more just the basics of black holes. In fact, I want to put on screen, because you've written a couple of popular science books about black holes, the most recent called The Black Hole Survival Guide, which is an impossibility, I guess, when you think about it. Spoiler alert, it doesn't end well. So what is the best way to actually understand what a black hole is?
Well, a black hole isn't, a lot of times we talk about a black hole in terms of how it forms. A star dies and creates a black hole. But a black hole is really something that can form in many ways. It's a warp in space-time that becomes so strong that not even light can escape. That's really what we mean about a black hole. So imagine a star. Just take an example of a star collapsing. A star, when it runs out of thermonuclear fuel, which keeps it afloat, will eventually begin to collapse under its own weight. And if it's heavy enough, which is much heavier than our own sun, our sun is not heavy enough, it will not be able to resist a kind of catastrophic gravitational collapse. And when the star becomes dense enough, it has deformed the space around it so strongly that light is taking a curved path that only leads inward to this collapsed star. And essentially, the star goes dark because the light, even from the star itself, cannot escape. Now, we call that region where that happens, when the stars become so dense, the event horizon. However, the star can no more sit at the event horizon than it can race outward at the speed of light. The star is forced to continue to collapse. And so it leaves the event horizon behind almost like an archaeological record. The star is gone. So if you are a space traveler, like in the survival guide, and you come near this region where light spills in, almost imagine space-time is like a waterfall at that point, falling inward. You would feel nothing, see nothing. It would be empty. So a black hole is actually a place in space that is completely empty. There's no material there. The star is gone.
Do scientists understand how they function in the cosmos?
More and more. I think in 1916, when Einstein first published his general theory of relativity, he receives a letter from a friend of his who's enlisted as an infantry soldier, even though he was a known astronomer, and is on the Russian front and has written down the first mathematical expression of a black hole. So for a long time, Einstein said, this is beautiful. He helps get the work published, but he thinks nature will protect us from their formation. He doesn't believe that they're going to occur in nature. It's really people like Oppenheimer, fascinatingly enough, because of his work on the atom bomb, begins to think about nuclear physics in stars and realizes that it's the same physics. And he begins to understand that stars are going to make black holes, that nature found a way to make black holes. And this is in the late 30s. And it's not until the 60s that people start to take it seriously. And it's not until the 70s that people start to see evidence of black holes. And since that time, there was, they fell in and out of fashion. They were considered exotic. People began to accept that they existed in the universe, but thought that they weren't that important. I think we understand now that about 1% of the stars in our galaxy will make black holes. So if we have 300 billion stars in our galaxy, that's a lot of black holes. And they're small. They're much, much smaller than the one at the center of our galaxy, which is supermassive. And we have no idea where those come from. Every galaxy that we know of in the universe, of which there are hundreds of billions, we believe has a supermassive black hole at its center. And we think that those black holes play a very significant role in sculpting galaxies, modulating their size, influencing the gas and the dust that leads to star formation by blowing jets out, by clearing material out. And again, we are in orbit around them. So they're the centers of maybe not our solar system the way our sun is, but they're the centers of our galaxies. And so we've come to understand that black holes aren't an oddity. They're actually really influential in the universe.
And based on what you've described, once formed, they are not static. They continue, they're very dynamic and continue to change.
Yeah, one of the beauties of the universe is that when we look into space, we're also seeing into time. We're seeing into the past. So the further away something is, the longer the light has taken to get to us, and the more that we're seeing deeper into the past. So it's possible that a distant galaxy looking at our black hole sees something called a quasar, which is an extremely energetic black hole that's extremely active. Now, that was billions of years ago. Our black hole was probably a quasar, extremely energetic, blowing out jets, and it has since quieted down. So we live 26,000 light years away. We're seeing the black hole as it was 26,000 years ago, but not billions of years ago. And it is quiet right now. But when we look into space, we see very active black holes as they were in the past. And right now, our black hole is quiet, but not completely static. So one of the reasons why the first black hole that was ever imaged was not our own, it was in a very nearby galaxy known as M87, Messier 87, was because that black hole is very, very, very quiet. It's big, it's far away, and it's not doing much. So taking a picture of it was easier, as difficult as it was, than taking a picture of our own, because over one night of observing, it might change enough that it's like taking a picture of somebody running around. So as quiet as it is, it's still active enough that it was a real challenge to take its picture.
Well, speaking of challenges, I wanted to have you add more detail to the creating of the image of Sag A star, because it was really quite a tale over many years.
Yes.
So, first of all, how far back in time did scientists know about the existence of a black hole in the center of our galaxy? When were we first aware of it?
That's an interesting question. I would say that the real evidence for it, I mean, there were suspicions, but the real evidence for it came from people like Andrea Ghez and Reinhard Genzel, both of whom were awarded the Nobel Prize for their work, by looking at stars orbiting the center of our Milky Way. And they were seeing stars over a period of like 16 years complete in orbit. So it's very diligent, very patient observing that they had to do. And what they realized is, just by simple, you don't even need to use very sophisticated calculations. You can estimate what it must be orbiting, the size and the heft of it. And they concluded, rightly, that it must be a black hole because it was extremely heavy, but extremely small. And so that evidence was pretty conclusive. However, we suspected this even before they concluded their observations. So the reason you make observations is because you have a hunch, right? And you don't just go out and look at anything. You go for gold. And just as a personal aside, Shep Doleman, who was the PI on this project, the principal investigator on this project, who announced the original image of the black hole in a nearby galaxy, was my roommate in graduate school. And so ever since we were kids at MIT, he's been talking about this. So it goes way back. I'm not going to say how many years, but it goes way back that people knew it was there, but wanted to prove it.
So he needed to put together a consortium of observers across the globe. Tell me how that project all came together.
I mean, it was a 20-year project. The idea, so I said that the black hole was very heavy, but it was very small. So you're taking something less than 20 times the width of the sun and you're pushing it 26,000 light years away. To our eyes, from our perspective, it's the size of a piece of fruit on the moon. Or as Shep Doleman phrased it, it's like reading the date on a quarter in San Francisco from New York City. And to do that, to resolve something so tiny, you needed a telescope the size of the entire Earth. Now, that might have made a lot of people quit. But instead, what Event Horizon Telescope Project did was they made a telescope the size of the Earth by combining telescopes around the globe and by using very sophisticated computational techniques so that while the Earth turned, it could observe the black hole with a bunch of different telescopes around the globe and then merge that data together as though it was a single snapshot taken by one camera. So like one eye the size of the Earth. And that was a really deep challenge. It took 20 years to iron out the difficulties, to understand which instruments around the Earth needed to be included to make that possible, and how to augment it by bringing new telescopes online. And also which light to look at, because the galaxy can be very bright if you look in the wrong light range. And so they had to try to find, to look at light where it was transparent. The galaxy would be more transparent to that kind of light. And it's just a remarkable achievement, really.
Did the opaqueness of the Milky Way add to the challenge?
Absolutely. There's a lot of, if you look at the Milky Way, the reason why it looks milky is because there's a lot of gas and dust that absorbs light and re-emits it. And so if you want to see past that milky rift in the sky, and it looks like a milky rift in the sky because you have to imagine we're in the plane of the galaxy. So we're seeing the galaxy edge on, right? We can't jump up out of the galaxy and look down on it. We don't have that technology. So we have to look through the plane of the galaxy. It makes it much more challenging. But the gas and the dust tends to absorb light and re-emit light in a certain frequency, in a certain energy band. And so if you try to shift your energy lower, which is what they did, they're looking largely in things like infrared and radio, where our eyes are no good, and the gas and dust is more transparent. if you shift out of the range of what our eyes can see. So it's kind of like putting on infrared goggles, and when you can see stuff that your eyes can't detect. But in this case, they went even lower than that. And it allowed for a transparency to look through the galaxy.
Now that the image has been released, are there more observatories wanting to come online and join the project?
I hope so, yes. And so there is a kind of what's called Next Generation Event Horizon Telescope, which is a project to build new instruments, because a lot of what Event Horizon Telescope did was it used existing instruments, and it begged and pleaded for time on those instruments, because lots of astronomers want to look at lots of things, and so they have to fight for time on the instruments. And so there's limited access to how much they can use. They can't freeze all other astronomy out, right? So maybe the night that they get the telescopes, the weather's bad or there's problems, So I think the next generation will be to bring new instruments online that are bespoke, that belong to Event Horizon Telescope, and will very much augment their resolution, their ability to see fine details, which is something that we want to hone in on. And there's often discussions also of going to space.
Well,
which would make an even bigger telescope.
Yeah, that's what I was going to ask, because the James Webb Telescope is scheduled to come online in the next couple of months. Will that be involved in the project?
I don't know. I don't think it's. I mean, it's unclear. I don't think it's not. It's conceivable that it will be enlisted. Again, the James Webb Space Telescope, lots of people are going to be trying to use it to look at different things. So it's conceivable it will be enlisted as a secondary instrument to also look at the black hole, but it itself cannot provide the resolution. You would need James Webb Space Telescope spread all over the place by itself. And also, it's not really quite the right lens for what you're trying to look at. But it could be enlisted as an instrument of support to support the observations. I think going to space would involve, it would be a very complex project, but it would involve also coordinating with the Earth-based instruments still.
You've described this past few decades as a big time for the understanding of black holes. I guess the question is, why are so many people interested and excited about them? What do they contribute to our understanding of our world?
We were talking about them as the collapse of stars, as astrophysical objects, but there's a sense in which black holes seem to be fundamental, more profoundly fundamental, meaning when we look at the quantum level, we hone in at the microscopic level, and we see, the universe appears to be made of these fundamental particles like electrons or quarks, and we can hone in even further, and maybe we'll discover more. Black holes share something in common with those fundamental particles, and that is utterly mysterious. They are flawless, meaning if I take a black hole and I throw Mount Everest onto it, I try to make it deformed and identifiable as my black hole because I've put Mount Everest on it and I can recognize it. It will not tolerate that imperfection. It will shed it off, and it will settle down to be a perfect, flawless, in some sense, unidentifiable black hole, featureless. And in that sense, they're fundamental to the universe in a way that I think we're still struggling to understand.
Studying black holes also enhances our knowledge of gravity, gravitational forces.
Absolutely.
And some of the reading I was doing for our interview suggested if we're living in the digital age, in the future, we may live in the age of harnessing gravity differently. What could that look like?
Wow. I mean, it's a lovely question. It is absolutely true. Black holes tell us something fundamental about gravity, that in some sense they are the terrain. If you are an explorer, intellectually, even in pen and paper, and you want to understand the fundamental laws of physics, especially gravity, you study black holes because they provide this terrain that reveals things about the fundamental laws of physics that we can't grasp in any other terrain. And so by stumbling around on this frontier, it gives you these clues that you try to piece together to understand gravity fundamentally. And one of the things that has come out of this program to understand black holes at the quantum level since Hawking and also Roger Penrose, is that they reveal something also at the quantum level, which is really surprising. So could we harness that energy? I mean, we can dream. But I think what we have to understand is the black hole harnesses that energy. And that's why we can see black holes several billion years ago on the distant edges of the universe, is precisely because black holes have figured out how to harness that energy. Can we harness it? I'm not so sure. But maybe it's okay that they harness it because, again, they've sculpted a universe in which we live. And that's part of what led to the evolution of human beings on a planet in orbit around a galaxy that harbors a black hole.
We have just 2 minutes left, and I'd like to close with understanding your motivation a little better. You started out studying, I understand, philosophy. How did you do your homework? How did you gravitate to science, and specifically astrophysics?
Well, so when I was in philosophy, I was drawn to the big questions. How, what are we doing here? What does it mean? How are we connected to the cosmos? These questions for me were not answered by philosophy. And in fact, I was extremely frustrated that we were spending hours discussing what some long past philosopher intended to mean when he said blah. I found that incredibly frustrating. When I was introduced to physics and mathematics, which was sometime in college, I thought, nobody's asking what did Einstein mean. When he taught us relativity, it belonged to us. It belongs to everyone who wants to learn it. It is theirs. And nobody who learns it is saying, what did Einstein mean? It's a gift. And I found that extremely transcendent and powerful. And I loved that it was true for me, and it was true for somebody in Bangladesh, and it's true for somebody in another galaxy. And I found that very meaningful, which is what philosophy was supposed to do.
Well, we're just about out of time. As we close, I want to offer 2 more resources of yours to them if people are intrigued to learn more. Once again, your latest book is a book that's the Black Hole Survival Guide. Spoiler alert again, not such a great ending. But also, there is a very fun video on YouTube to recommend to people if they want to learn more, and that is you explaining black holes to people of very different ages, from a child all the way to someone who works in the sciences. And that's a great way to get a better introduction and maybe have a conversation with people who are just beginning to learn about them. Thank you very much for spending a half an hour with us.
Thank you so much, Susan. It's a pleasure.
Q&A's conversation about space science continues next in a conversation with Dr. Jessica Whiteside on the exploits of the Mars rover Perseverance.
Current speed is about 30 meters per second, altitude of about 300 meters off the surface of Mars. We have started our constant velocity accordion, which means we are conducting the sky crane, about to conduct the sky crane maneuver. Sky crane maneuver has started, about 20 meters off the surface.
We're getting signals from MRO. Tango Delta.
Touchdown confirmed. Perseverance safely on the surface of Mars, ready to begin seeking the signs of past life.
That's NASA video of the Perseverance rover landing on Mars, February 18th, 2021. Dr. Jessica Whiteside is one of the many scientists who've been watching the rover very carefully and excited about some of the news that it's been making back here on Earth, and is here to explain what's happening and its significance. So this rover is titled the Perseverance, and one of the big moments that it had in its year-plus mission is that it's begun a climb and rock sampling collection. This is your bailiwick, so tell us about what the Mars rover is doing and why it matters.
Right. So when we look out at Mars at the night sky, we see a red ball. It looks like it's cold and barren, a frozen dust ball, and pockmarked with craters. But actually, 3 billion years ago, it was a blue world. It was a watery world just like Earth. It had an ocean that covered nearly a third of the planet. It had bountiful lakes on land. It had rivers and ponds. And what Perseverance has done is it's actually now approached one of these lakes It landed in the lake, and it's been desperately, longingly, lovingly staring at the delta. The delta is its main astrobiological target. It's meant to be an astrobiological feast, and that's because deltas here on Earth are some of the most abundant areas for life itself. So that's what these are. These are sedimentary time machines transporting us back 3.7 billion years ago. Again, when Mars was this watery world, possibly life existed there, and that delta is critical. That's the main point, really, that Perseverance is there, is for that astrobiological target. That delta is so critical. We know deltas here on Earth are the hot biodiversity spots. You know, it's been said that there are 1 million times more bacteria in the soil than there are stars in our sky. And deltas represent one of these hot biodiversity hotspots. You can think of them, if you remember from high school, the ancient Egyptians, they were capitalizing on the Nile Delta. They were the first in agriculture because it's so fertile, the soil is so beaming with life, and that's why this is such a critical target. So these deltas form where there's a fast-moving river that empties into a still body. In this case, it's a 25-mile across crater, so that's about the size of Lake Tahoe. This lake, this fast-moving water hits the still water and dumps everything into that. So it's important in terms of life, because if there's life, it's throwing in nutrients, which will allow for more blooming, more abundance of the life. And also it's important because it's scouring the landscape as it's moving into that lake. So it's picking up the nutrients along the way. It's picking up any life that might be on land along the way. And it's bringing, very importantly, sediments like silt and clay with it that it dumps in. So it's important both for the production of life itself and the preservation, because that rapidly buries into the lake like a layer cake. If you've made a cake, very quickly, rapid entombing life, if it was there underneath that clay and sediment. So that's why this is such a key landing. When you look at the site, it looks like a mound of red rocks and dirt. But if you know how to read the rocks, and Perseverance does with its multitude of cameras and different types of equipment on board, it's basically a Swiss Army knife running on wheels. So it has a payload with lots of different types of cameras and spectrometers and lasers that can vaporize rocks and map organic or chemical constituents. So that's why this delta is so critical in the search of life on Mars.
In addition to pictures right now, what can Perseverance send back to Earth for scientists such as yourself to study?
So Perseverance has been sending back data on chemistry, so it can actually get information that's as fine as what's in essentially a grain of salt. So a lot of chemical data being sent back. Now, that's not to say that it's chemical data that is necessarily indicative of life, but it tells you something about the landscape there. It tells you something about life-favoring conditions or what that water was like.
It's also collecting rock samples as it works, and these, I would imagine, have a limited capacity, how many it can collect. How are the decisions made along the way about, yes, this is one we want to core and preserve?
Well, this is the critical question, to collect or not to collect, and that's why Perseverance has now gone up to the delta. So it's actually going to do reconnaissance for some time and collect samples on its way back and use all of those multitude of equipment on that Swiss Army knife with wheels. So the laser vaporizing, the rock vaporizing lasers, the mapping of any kind of chemical or organic matter, all of the cameras, to deduce what the key areas that might have the best likelihood of preserving life. It's actually only going to collect about 3 samples while on the delta before bringing them to the bottom of the delta and leaving them there for a future rover to actually collect, and something akin to an interplanetary Easter egg hunt.
Those samples are not slated to return to Earth until the 2030s. Why so long?
That's because it takes quite a long, it will, so the samples aren't due back for another decade, and that's because this is just the first chapter in a trilogy of events that need to happen to get those samples back. Perseverance is collecting samples. It'll leave those samples on the surface of Mars, and then the next 2 chapters will come about. Those chapters involve another rover that comes, a dune buggy fetch rover, that like an interplanetary Easter egg hunt will collect the various samples that Perseverance has been leaving behind. There'll be about 41 in total. Each sample is about the size of your little finger, your pinky, and the total payload coming back, the total amount of samples about the size of a loaf of bread. There will then be another rocket that goes out to collect there'll be another rocket that goes out that the fetch rover will meet up with and actually drop off the samples to that rocket. They will be propelled into orbit for the third part of this story, which is an orbiting satellite that will collect those samples. It will actually catch them essentially in its belly in space, needs to find them, and then they will be brought back to Earth and sent into the deserts out in Utah, landing in parachutes, and then dispelled across the world into various laboratories. So again, all of this excitement, all of this work, and this great technological miracle that involves this interplanetary carnival act where you need these various other pieces to actually bring the material back to Earth where it can safely be disseminated into those various labs.
One of those tools on this, as you call it, Swiss Army knife of a rover that Perseverance is an onboard helicopter. The first time any of the rovers have had that. And I've seen some interviews where you are really very excited about what this helicopter is able to do. Tell me about its name is Ingenuity. What does it do, and why are you so excited about it as a scientist?
Well, Ingenuity is another demonstration of the technological miracle that we come to expect from NASA. Now, this was really a David and Goliath moment. Ingenuity hitched a ride to Mars in the underbelly of Perseverance. And after 44 days of being sheltered, it basically was born in a reverse origami fashion, like a calf coming out of a cow. It crawled its way out, stayed on the surface for a while, and then did its first test flight, which was not only successful in that first test flight, but it's actually taken 28 flights, so it's actually continued to exceed expectations. Now, just to think about that little helicopter itself, it's about the size of a cantaloupe. It weighs only about 4 pounds, and it has very, very light copter blades, so they're only about the size of a piece of toilet tissue, actually, and it's able to withstand the 99% the 99% less dense atmosphere of Mars. So Mars has a very thin atmosphere, just a wisp of an atmosphere. The Earth's atmosphere is 99 times thicker than the atmosphere on Mars, which means that this little robocopter had to surmount all kinds of trials and tribulations to actually take flight. So the blades itself are rotating about 10 times faster than any blades would be on a helicopter on Earth. Its flight was the equivalent of an airplane flying 2 times higher than Mount Everest, double what it normally flies in the atmosphere, because the atmosphere is so thin there's nothing really for it to grasp into. There are also all kinds of other technological adaptations to allow this thing to fly. It's been said that it was essentially, to even keep it flying, maneuvering, you had to take into account it would be something like on Earth if you were riding your bicycle, but put your backpack and all of your shopping groceries on the front handlebars and try to think of how you would keep that sustained actually on ground. But this is happening in the air. So it's not just the atmosphere itself that involves needing much faster blades, a much lighter instrument to actually fly, but it's also the conditions on Mars itself. So that little helicopter, before it even took flight, had to withstand the very cold temperatures of Mars. So it had to go through freezing nights. Even during the daytime, the temperature difference at Mars is substantial. Because it lacks an atmosphere, essentially has this very thin atmosphere. If you were standing on the equator at Mars in daytime, your feet would basically be in spring and your head would be in the dead of winter. So your head would be freezing. So it had to actually be able to account for that as well as it takes flight and actually goes vertical into the air. So it's just an amazing feat that this thing took off. I think even 10 years ago when people were talking about trying to put a copter alongside Perseverance as potentially a sidekick, as a navigator, there was a lot of dismissal that this could even possibly take flight. I mean, we've only been flying here on Earth for over 100 years, and here we were going to take flight on another planet, a planet that's nothing like Earth in terms of its modern conditions and has that very, very thin, wispy atmosphere. So Perseverance, taking Ingenuity's birth, and then not just the first flight, but actually these 28 different flights, each one surpassing the other in terms of the height into the Martian atmosphere. It's absolutely amazing. It's also amazing because it paves the way for further opportunity in terms of bringing copters on remote intergalactic areas. So on other planetary bodies or lunar atmospheres, there's even another mission that's already planned for Saturn's big moon of Titan that has hydrocarbon lakes and ocean. So there's going to be another copter that goes out there, and eventually possibly copters that go out that are also Swiss Army knives in the air that are able to actually collect samples from areas that the rovers can't get to. I'm really excited about Ingenuity for its potential to be another one of these life hunter robotic instruments that's deployed on planets looking for biosignatures of life. So what I'm really excited about is that it paves the way for not just going across the terrain, which is what the rovers are doing, but going up to surfaces that might be actually harboring active life on Mars. And that is an area that's very steep, that are on cliffs that are called recurring slope linea, where you have vertical streaming, basically briny water that turns colors based on the season. So sometimes looks a little black, and this is known from orbiting satellites that are saying the albedo or the reflectiveness coming back into space, suggesting that at times it's white and at times it's darker, which is something we know here on Earth happens in terms of the seasons and productivity in water bodies. So that's why I'm very excited about Ingenuity, is its potential as yet another but this time even more capable, at least in terms of some of these areas where rovers would not be able to get, and where we might not want to send a human in the future because of planetary protection that is contaminating any potential life on Mars with Earth life.
Well, I'm going to try and hope this works, because I wanted to have people listen to another one of the tools in the toolkit, and that is the microphone on board Perseverance, which has been capturing the sound of wind on Mars. We're going to play a clip of that so people can hear what it sounds like. Dr. Jessica Whiteside, some of the news reports suggest that one thing that scientists have learned from the wind study is why the planet looks red to us.
Yes, that's right. So when we see Mars from a distance, it certainly looks red, and looks red because it's stained with a certain type of iron oxide called hematite. It's the same principle if you've ever left your bike outside or a pair of roller skates and come back to find them red. So that's oxidized red, insoluble in water, so rustiness. Now that wind is basically, the weather on Mars is controlled by the wind. Unlike on Earth, it's really controlled by water, because we have a vertical hydrological system where water is coming up in rain and coming down in through groundwater, and then the cycle starts again. In Mars, really, the weather is captured by the wind. So you heard that for the first time, and that's another one of the amazing breakthroughs that Perseverance has, is that it has those two microphones that are breaking ground. Those past rovers, that whole fleet, Curiosity, Sojourner, Spirit, and Opportunity, they have seen, touched, tasted, and smelled Mars in whatever way, a robotic manner one would see, touch, taste, and smell Mars. But here we have actually soundscape on Mars, demonstrating that what we see as the red is really being blown by actually dust. And it also goes into play that we know also that there are these fantastic dust storms that happen on Mars. So something similar to dust storms that happen out in the American West and Southwest, but something orders of magnitude bigger. You can actually have dust storms that cover half the planet. And one of these actually took out the rover Opportunity in 2018. But yeah, it's fantastic that now you can actually hear what Mars sounds like as well.
As you've described, it's the 5th Mars rover deployed by NASA. Give people a sense of how large the vehicle is if they were to see it with their own eyes.
All right, so it's about the size of a SUV. It's much bigger than the other rovers. The first rover was about the size of a microwave oven. This was Sojourner that went out in 1997. Sojourner was able to demonstrate that rovers could rove on the planet. And then there was Spirit and Opportunity, the twin rovers that set out, and they were able to find evidence of water. And that's become NASA's mantra, that in the search for life, follow the water. Curiosity picked up on that, and Curiosity headed out and did find water, ancient water, in Gale Crater. And it also found something very interesting in that crater, which is organic compounds, which is really tantalizing in terms of there being evidence of past life. And now here we have Perseverance. It's gotten even bigger, and the wheels have gotten much thicker with a better tread. Perseverance superficially resembles Curiosity, but it has much more sophisticated instruments on its payload, and very importantly, for the very first time, has that ability to actually take samples that will be brought back to Earth for the very first time.
What is its anticipated lifespan?
Well, the mission itself is for Perseverance to rove around the planet for 2 years, but as NASA has shown with the sister rovers, they have outlived and exceeded their expectations.
Is the United States and NASA the only country that is exploring Mars?
No. So in terms of even the sample return is a joint initiative between the United States, NASA, and the European Space Agency. There's also currently a rover on the planet that China sent out.
So can you help people understand why the study of life on Mars, or study of Mars itself, is valuable to humankind?
This is a fantastic question. So ever since Galileo looked through a telescope and saw Mars, it has fascinated the public. It has fascinated people in terms of if there's life outside of Earth within our solar system. Now, it's not just a philosophical or existential question, are we alone in the atmosphere? But there are very important implications if we do find life on Mars. One of them is that we would then have follow-up questions in terms of, did life originate first on Earth or on Mars? Because if life is the same age on both planets, there are implications that possibly all life on Earth actually came from Mars. That is, that Earthlings are actually Martians, and vice versa. It could mean that if there was life on Mars 3.7 billion years ago, when it was a blue world with all of that water, then there was life on Earth at the same time that possibly that life on Mars came from Earth. And the way that would work is we know from our own landscape that there are several instances when Martian meteorites have smashed into our planet, leaving evidence behind, leaving those actual rocks. So there could be transport of life between the two planets. It's all very fascinating. There are endless questions in terms of what it means for life on Mars, life on Earth at the same time, and that interplanetary confluence, fertilization between the two planets.
Your current academic posting is at the University of Southampton in the UK. What is going on at your university? Why did you decide to go there academically, and what kind of work are you and your colleagues doing with this information?
Well, I decided to go to the University of Southampton actually while on a 417-foot-long ship known as the JOIDES Resolution, which is the American ship for the International Ocean Discovery Program that basically goes out across the world's oceans, answering questions in terms of how various parts of the ocean formed, in terms of past climate change, in terms of limits of habitability in the ocean. And I was there to understand the formation of the Western Boundary Current. This is the boundary current that actually allows for ice formation in the North Atlantic that created the iceberg that actually sank the Titanic. And one of the co-chief scientists on this expedition was from the University of Southampton. So in essence, I had 2 months of essential proselytizing about the University of Southampton, and there was an opportunity to go and establish an organic geochemistry laboratory to look at limits of habitability of life here on our Earth, especially after major mass extinction events where extreme climate episodes wiped out various parts of life and various parts of the planet, in some cases globally. And it's the sequelae of the reestablishment of life after those that my work was focusing on. Now, a twist of that now is that we're very interested in astrobiological pursuits. So we're very interested in developing biosignatures to understand how life develops after mass extinction events, but also how we can tag for the chemical, and not just chemical, but molecular evidence of life and other planets. So it's been said that diamonds last forever, but molecules, that is fossilized hydrocarbons, also last forever. And so we're trying to build up a suite of these biomarkers, these biosignatures, to potentially look at life on other planets like on Mars. So right now we're canvassing various terrestrial analogs, so places on Earth that are similar to some of these areas like Jezero that might harbor life. So these very hypersaline, very high pH lakes with interfering deltas here on Earth, and trying to get as robust signatures as we can in order to test on future sample return.
I read a Q&A about you, and you told the story that you got interested in science at the age of 15. Can you tell me what prompted the direction of your career?
Sure. So I was very fortunate to have grown up in various states around the U.S. So we actually lived in 26 different states. And my dad was an amateur geologist of sorts. He was very keen on understanding how mountains form. So it wasn't just a story of rocks were laid down like this and then they get overturned, but it was the whole narrative involved in terms of what these rocks meant. Now, I grew up, in the back of a station wagon, basically reading various books. I thought I was going to be the next Joseph Campbell. I was very interested in world mythologies, and especially comparative world mythologies, particularly those on creation myths or the origin of life. And when my dad explained to me the first fossils that I had seen, which were out in the very bottom of the Grand Canyon, actually, it was such an epiphany to me that there could be a field that explained with tangible existence a story. So this idea of sedimentary time machines where you can look at a rock and be transported back on Earth 500 million years ago, 200 million years ago. In the case of Mars and Perseverance, transported back 3.7 billion years ago to a drastically different world, and be able to infer all the events that culminated in that particular rock that you saw. So it was such a beautiful thing to me that there was something that had a physical, tangible existence that backed up this idea of comparative world mythology. And I never really looked back from there, other than to say that my work has gotten increasingly smaller. So from looking at big landforms to chemical or isotopic signatures, and then to molecules themselves.
You also, I understand, had the opportunity to attend a STEM school in Arkansas as a teenager. So much debate in Washington, D.C. about STEM schools. What would you have to say about the experience and what it did for you?
It was a life-changing experience for me. I went to the Arkansas School for Mathematics and Sciences. That now includes arts as well. I was in the third graduating year, and it was absolutely tremendous. We had residential mentors who would drive us actually to various facilities, and it was all about paving your own way. So if you had an idea for a science fair experiment, then they helped facilitate, they helped catalyze that. So very importantly for me, I was able to work on two very different projects, one at the University of Arkansas Medical Services and one at the University in North Little Rock. And I was actually transported there almost daily to work in the chemistry labs. And not only did I get to work in the chemistry labs, I was able to associate with the graduate students in those labs, with the professors in those labs. I was even able to blow my own glassware in my first year. And it was a tremendous experience. One of those projects was on trying to understand low-level microwave radiation and the growth of plants. And this was, just as an observation of driving, again, all those 26 different states in the back of a station wagon, and noticing that there tend to be an awful lot of life underneath power lines out of the car window. And so I was able to test that in small controlled experiments. And then another one that was looking at titanium dioxide, the pigment that makes toothpaste basically white. And also, if you have ever seen out behind airplanes when it leaves messages, that white is written with titanium dioxide. But using titanium dioxide as a potential photocatalyst to break down hydrocarbons. So in other words, using it to kind of speed up something equivalent to photosynthesis, but to break down waste products in water. So for me, it was a fantastic experience. It gave me the confidence that I needed. I went in as someone who was a twin sister, but the younger twin sister, and also someone who grew up with 24 foster siblings in my family. And I was very shy and quiet, and I came out a very different person. So I'm all for STEM schools. It really helped pave the way for my future career.
So from a STEM school and in your high school years now to one of the thousands of scientists around the globe who are studying the work of the Mars rover, thank you so much for bringing us up to date on the latest discoveries. And I know there'll be more that we'll be watching back on Earth as it continues to send data and pictures back to all of us. Thanks for your time.
Thank you.
Thanks for listening to C-SPAN's Q&A, and subscribe to us wherever you get your podcasts so you'll never miss an episode. And while you're there, please take a minute to rate and review us. You can also send us an email about Q&A at podcasts@c-span.org. Send me your questions, your comments, or ideas. Your feedback is welcome.